The next distribution function will be the exponential distribution. Let's say that you are looking at a phenomena where a certain event happens at a number of times per hour. Let's say that you look out of your window and you see on average 2 cars pass by per hour. Sometimes you will see more per hour and sometimes you will see less per hour, but on average it will be 2. Now, if you measure the time interval between these events, for instance, in the car example, if you measure the time between 2 cars passing and collect all of these data points, then these will be distributed according to an exponential pattern. It will start out very high and then it will quickly taper off. And this function only takes in one parameter, namely the scale or the decay rate. Now this will be the average number of events per time interval. For instance, in the car example, this will be 2, because on average you see 2 cars per hour. And you can understand the shape of this distribution by realizing that longer waiting times between events become much more unlikely. Let's say, for instance, that you have 2 cars per hour, then a time interval between 2 cars passing of, let's say, 10 hours will be incredibly unlikely. And it is in this way that we can also understand the single parameter of this function, the scale parameter. If this parameter increases, meaning more events happening per time interval, then this distribution function will fall off much more quickly. Because if you have much more events per hour, then that means that on average, you will also have much shorter time intervals between events, and thus larger time intervals will become much more unlikely. And this also immediately brings us to the fact that the average of this distribution will be 1 over the scale of this distribution. Now, why is this? Well, think back on the car example. If you see on average 2 cars per hour, then the average waiting time between 2 cars passing will be 1 over 2 or 30 minutes. And this makes a lot of sense. Now, if we look at the cumulative distribution function, then we see that the slope is enormously large at the start, and then it tapers off exponentially. Now, this of course reflects the fact that most of the data falls with lower waiting times, and thus in the front of this distribution. In code, this is very easily replicated. The exponential distribution, as we saw, only requires one parameter, namely the scale. Thus, a new Python array, exponential distribution, is numpy.random.exponential, and the only parameter is the scale, and of course, the number of elements that we want to generate. So let's now go to the next distribution.